Hi and welcome to our next edition of our P4 Radiation for Life. Now in this edition, video we'll be looking at the uses of radiation, so how we might be able to use alpha, beta and gamma sources for everyday life. Okay, so let's have a look at our objectives for this lesson. We're going to be looking at the uses of radiation, so by the end of this lesson you should understand how alpha, beta and gamma radiation can be used in a variety of different ways. Background radiation is naturally occurring radiation. It's around us most of the time and released by radioactive substances around us, such as things in the soil, from cosmic radiation from space, and from local rocks depending on the area you live in. So this picture of Dartmoor is very heavily radioactive because of the amount of granite, as will places like Aberdeen. Now, it's not just the natural radiation that gives us background radiation. Hospitals and factories can also provide a background radiation level. So things like radiotherapy and X-rays may contribute to some of that background radiation. Now there are a couple of types of tracers. You can use them in hospitals, you can use them in industry where they can look for the dispersal of waste and the blockages in underground pipes, and you can find out the roots of underground pipes. Now you might have seen this perhaps at home, where you can put a radioactive tracer into a water system and then you can trace where it actually goes out to. So perhaps you've got a river where you're looking at who's polluting it, so you put radioactive traces in the water and that should hopefully find out where it goes. One of the bigger uses is for trying to find leaks and blockages in pipes. Now you can see here that this pipe is underground. Now it would obviously cost a lot of money to employ these four blokes and to dig out the pipe. So what they can do is they can put a radioactive tracer into the water system that will go through the pipe. Now because this will be a gamma ray, the gamma will be able to move out of the ground so it can be detected. Now if there was a blockage, let's say here, then there would be no tracer along here, so they could say, right, let's dig up this section and we can change this. Also, if they were starting to get radioactive traces here, then they could say there's a leak here as well. Now, other than in industry, radioactive sources can also be used in hospitals. Now, for things like a PET scan, radioactive sugar is introduced to the body. Now, because cancer, which is where you might often have a PET scan, feeds off a lot of sugar, you can look at where the gamma rays are given off and you can see where there are areas of red. These might be where there is high heat, which means there's a lot of respiration going on, and that's what a PET scan is. So this is obviously for a brain, but you can also have full body scans that might also give an indication. So you've got the gamma ray being given off by the tumour here, and then it's obviously detected, and then you can pinpoint where that tumour actually is. Now smoke alarms use radioactive material, and they use americium-241, which is a radioactive isotope that emits alpha particles. Now alpha particles ionize things very easily, which means they lose that positive charge that they have. Now if we look at this diagram, we can see here that we've got the americium-241 here, and that emits alpha particles down here. Now here you have a potential difference going around here. So here's your battery and here's your alarm that will make a noise. Now, as the americium comes down here, it removes electrons from the air, and what that does is it creates a circuit going around here. Now, if we get smoke coming up through here, what will happen is the smoke will ionise rather than the air, meaning that the current going around this circuit will be lower than normal. And what that will do is that will make the alarm sound. So when we get a normal current, no alarm, and then when we get a low current, that's when the smoke alarm will go off. Carbon dating can be used to see how old things in the air and living things are. Well, not living anymore. Now, all human and life forms, whether they're plants or animals, will contain carbon, and a small percentage of that carbon will be known as carbon-14. Now, carbon-14 is radioactive. Now, it has a half-life of 5,700 years, which means if we can tell how much carbon-14 is there from the original sample, which we know roughly to be a certain percentage, we can find out how old it is. Now, all living material contains carbon-14, so we can find out how old something is by looking at the number of half-lives that have gone by since the item was there. Now, dating rocks is not where you get a bit of granite and a bit of limestone and they go out for a dinner and a cinema and perhaps something more. This is where they actually find out how old rocks are. Now, we know how old the Earth is by using this method. Now, uranium has one of the longest half-lives of 4.5 billion years old. Now, we know this because this is the age of the Earth. Now, uranium decays, so we know that since the beginning of the Earth we've had one half-life of uranium decay, and that's how long the rock that we live on will be. So uranium has a half-life of 4.5 billion years, which is the same age as the Earth, and that's for uranium. Now, radioactivity can be made synthetically. Now, here we have a stable nuclei, and here we have a neutron. Now, what we can do is we can take this neutron and fire it into the nucleus there. Now, this can make it unstable, causing a beta particle to fly out. Now, along with that, we might get some gamma radiation as well. Now, we can use this type of radiation in hospitals. Now, we can use it as X-rays, or we can use it as gamma rays. Now, you will notice here that the gamma ray is a lot smaller wavelength and higher frequency than the X-ray. Okay, but in reality there's not really that much difference between them. Now, with X-rays will pass through soft tissue, so we can actually create an image of the bone inside, whereas gamma rays are more penetrating and can actually pass all the way through. Now, when you may have had an X-ray or been treated with radiotherapy, and what the person that's doing it will do is they will often hide behind a lead wall, and that's to protect themselves from the radiation. Now, an X-ray is around about 20 times more powerful than background radiation. Now, the gamma rays are used normally for treating cancer. Now, what they do is they pass through the skin and they target the cells, and what they do is they can damage the DNA within the cell and cause it to not be able to replicate, and therefore reducing the spread of the cancer. Now, it can also be used to sterilise medical equipment, as for the same reason it can kill bacteria and any other germs that might be there. Now, it's all important that when we're doing any of this that we select the right radioactive material, so knowledge of the half-life is extremely important. Okay, so we have looked at the uses of radioactivity. We've looked at several different things. We've looked at the use of tracers in hospitals and in industry. We've looked at the use of americium-241 in smoke alarms. We've looked at carbon-14 in carbon dating and uranium for dating rocks. We've also looked at the uses of X-rays and gamma rays in medical physics, in hospitals for gaining images and treating cancer. Anyway, that's all for this lesson, and I will see you next time. Bye-bye. Bye.